What kind of mathematics describes how a system changes from an initial state to a final state when acted upon by an operation? For example, imagine an aircraft flying in the sky. Its position and orientation at one moment is the initial state. If the pilot performs an operation, like rolling towards the right while moving forward, the aircraft reaches a new position and orientation, which is its final state. How can we understand and describe these changes systematically? Algebra is the mathematical language to answer these questions. The word algebra comes from the Arabic term al-jabr, meaning reunion of broken parts. Algebra is a branch of mathematics that deals with abstract systems. It uses letters and symbols called variables to represent unknown or changing quantities, making it a generalization of arithmetic. In our context, the broken parts are the initial state of a system, the applied operation, and the resulting final state. Algebra studies how these pieces fit together. Linear algebra is a language to describe linear transformations. It is the study of systems where operations behave predictably. In a linear transformation, scaling an input scales the output proportionally, and adding inputs produces outputs that add up in the same manner. When extended to include translations, it can also describe shifts in position, capturing both linear changes and movements in space using vectors and matrices. Using the aircraft's example, the full operation can be understood as the combination of first rotating the aircraft along the horizontal direction and then moving it forward. These operations can be described by linear algebra. This predictability appears in many real-world systems, which is why linear algebra has such a big role to play. Now we will go through examples to introduce multiple aspects of linear algebra. We will visit these examples in greater details in later videos. Let's look at our aircraft again and track the tip of its wing. We need a set of axes to define our reference direction. We label them as the x, the y, and the z directions. Using these axes, we can describe the position of the tip of the wing using a vector. Vectors represent all the information needed to describe the system at a given moment. The initial position of the tip is shown by the vector A. To reach its final position, we have to first apply a matrix multiplication to rotate vector A around the x-axis. Once we have achieved the rotation, we can account for translation by adding another vector t. The wingtip ends up at a position B, which is the final state after the combined operation. The concept of a vector isn't limited to physical space. It can also describe other physical processes. For example, it can describe sounds. Imagine a pure tone, a simple wave of a single frequency. That's one of the vectors that forms the basis of the vector space of sounds. Now, when we combine another pure tone with our original tone, we get a richer, more complex sound. This combination of adding one wave to another is an example of vector addition in this particular vector space. In fact, any complex sound can be broken down into a combination of pure monotones, each contributing its own amplitude and frequency. This representation is called Fourier space, where each pure tone serves as a direction in our vector space. Imagine a collection of arrows. Now apply a stretching operation in a certain direction. Most arrows change direction, but a few special arrows remain pointing along the same line. These arrows are called eigenvectors. The factor by which each eigenvector stretches or shrinks under the operation is called its eigenvalue. Eigenvectors and eigenvalues are defined relative to this particular operation. Eigenvectors reveal the direction in which a system changes predictably, even when the overall transformation looks complex. They are fundamental concepts in linear algebra used in applications from stability analysis to vibrations. Often we want to understand an operation or physical process, and we have information about the state of the system at various times. Imagine our pilot tracking the banking angle of the aircraft and taking 10 measurements, one every second. Each measurement appears on a scatter plot with time on the x-axis and banking angle on the y-axis. By examining all the points together, we can uncover the underlying operation, how the aircraft's banking angle changes over time. Linear regression finds the best fit line through these measurements, showing the trend that approximates the aircraft's motion. This demonstrates a key idea in linear algebra. Sometimes we know the outcomes and want to discover the transformation that produced them. In real life, this approach is useful for predicting motion, analyzing trends in data, or understanding physical processes from observations. Often, we are faced with large and complex systems, and we want to understand their essential structure without getting lost in every detail. Imagine a black and white photograph. Digitally, this image is represented as a large grid of numbers, each number showing how bright or dark a single pixel is. That grid is our initial state. Singular value decomposition, or SVD, acts as the operation that breaks this large grid into simpler parts, uncovering the underlying structure of the image. It separates the image into layers ranked by importance. The largest singular value captures the main features, the broad shapes and contrast, while the smaller ones hold the fine details and noise. By keeping only the few largest singular values and discarding the rest, we can reconstruct a final image that looks almost the same but requires far less data to store. This idea of reducing complexity while preserving what truly matters extends far beyond images. It's the same principle used in data compression, pattern recognition, and modern machine learning. These examples illustrate the power and reach of linear algebra. From physical systems to sound, stretching, motion analysis, and images. In the next video, we will begin exploring vectors and vector spaces, which form the foundation of linear algebra and allow us to describe systems and transformations mathematically.